9.3 is talking about exponential functions and their graphs. So we're going to do a couple of things here. We're going to graph exponential equations and exponential functions. And we're going to solve some applied problems involving exponential functions and their graphs. So the function f of x is equal to a to the x power, where x is a real number and a is greater than 0 and not 1, is called an exponential function. It has the base of a. The base needs to be a positive in order to avoid complex numbers that would occur by taking even roots of negative numbers. So let's talk about some of this stuff. One of the most, I actually think exponential equations are one of the most common things you run into in real life. Because anytime you're talking about compound growth, like with a bank, or you're talking about when you're investing your money and you're talking about it increasing at an exponential rate, you're talking about an exponential equation. So if something is growing exponentially, we say it's getting really big, really fast. The other side of that is could be exponential decay. So you'd start out with something really big and it would get really small really fast. Okay. This time of year, you all are grown-ups, but when you're a kid, and some of you probably still get this question from your parents, but they start asking you around Thanksgiving, like, what do you want for Christmas? Or I know I ask my people, like, what am I supposed to be getting you for Christmas, right? And so I try to get people to say, well, tell whoever it is you want 1 penny today and 2 pennies tomorrow and 3 pennies and 4 pennies the next day, and have your pennies double for 30 days. And that's all you want, right? So if that were to happen, okay, this would be an example of an exponential. You would get on day 1, right? You would just have 1 penny. So you're at 1 cent. Day 2, you would have 2 cents because we're just doubling this. Day 4, you would have 4 cents. What's going day 3? I'm sorry. Day 3, you would have 4 cents. Day 4, what are we at? 8. Okay. Doesn't look like we're making much progress here, right? But if I want to figure out what I'd have on day 30, is there some kind of an equation that I can come up that's going to do this for me, right? So we don't want to have to keep going. We don't want to have to keep doubling this to day 30. So if I wanted to get this, I could use, I'm starting out with, and we're going to talk about this stuff in a minute, but I'm starting out with 1 cent. And what I'm doing to that 1 cent is I'm doubling it every day. So I'm multiplying it by 2. I'm doubling it every day. And the X would be the number of days I was at. So let's just see if let's go back and make sure that we're working. We might need to subtract a 1 from this. So day 1, if I plug in a 1 right here, I would get 0.01 times 2 to the first power, which would be 2. So this would really be figuring out day 2. So we need to subtract 1 right here to get to actually get our answer that we would come up with. So we would get 0.01 times on day 2, we would say 2 minus 1. So 0.01 times 2 to the 2 minus 1, which would be to the first power, that would give us 2 cents. Okay, are y'all good with this equation? So if I want to figure out day 30, what I would do is I would say 0.01 times 2 to the 30 minus 1. So that should give me what I would have in pennies if we did this. So let me go to the graphing calculator and let's type this in real quick. So we've got 0.01. We're starting out with 1 penny, but on day 30, we would have, we're raising that to the 29th power because we're subtracting 1, right? So we're saying 29 here. And I'm getting this number. So 5368709.12. If we go backwards and we look at our commas, we have a comma before the 7 and a comma before the I'm sorry, right after the 5. So 5,368,000 $709.12. So you just drop that down. So on day 30, we would have $5,368,709.12. Not bad, right? And that would just be day 30, because really with this plan, you'd have to go back and add up all the days before that. So that would be a whole lot of money. And I used to teach middle school several years ago, and I would have my kids go home and tell their parents, like, this is what I want. And there would be a couple that would come back and they said yes. I was like, well, they may have said yes, but I don't think they're going to be able to follow through with it, but maybe that would be great. So this is an example of exponential growth, something that starts really, really small, but it gets really, really big, really fast. Okay. The other thing in this is exponential decay. And exponential decay happens when you've got something really big and it's getting really small really fast. A lot of times we talk about exponential decay in your chemistry class when you're talking about half-life. If you keep taking the half of something, it's going to get smaller and smaller and smaller. If you go to the hospital and you get an IV of drugs, of whatever kind of drugs, they're going to want to know how long does it take that drug to get out of your system, and they'll talk about half-life there too. So that would be an example of exponential decay, and I'm sure there's lots of other examples. So we've got some exponential functions down here, just some examples. If you'll look at every single one of these, what is the exponent? X. That's exactly right. So if you look at every single one of these, you have X as an exponent. The number that is raised to the X power, that is your base. Okay. So graphing exponential functions. We want to compute some function values and list the results in a table, and then we're going to plot those. That's not anything new. And in fact, a lot of the time, what we do is we go to our graphing calculator and we would type in y equals 2 to the x, and we would go to our table. Except this could be a little bit tricky whenever you're dealing with exponential. So because your table might give you a decimal and you might want the fraction form. Okay, so let's just go over, in case that happens, what would we need to do? So they're telling us every time what our X value is. I'm going to go ahead and just put this down over here. Okay, and so every time they're saying they want us to raise 2 to whatever power they've got for our X. So 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. And most of you are going to be really good with this 2 to the third and 2 to the second and 2 to the first, but we haven't really talked about what it means to have this things raised to the 0 power and to the negative 1 and to the negative 2. So let's make sure that you understand what you're supposed to do with that stuff. You can just type it in your calculator and it's going to give you an answer, but like sometimes you're going to want the fraction and you're going to want to understand why it is the way it is. So we know 2 to the third means 2 times 2 times 2, which is 8. We're good with that part. We know 2 squared is 2 times 2, which is 4. Okay, and we know that 2 to the first power is just 2. So we could go ahead and plot those points: 3, 8, 2, 4, 1, 2. Okay, so here's what I want you to think about. Here, the answers are 8, 4, and 2. what could you do mathematically that would get you from 8 to 4? What can we do to get from 8 to 4? We could take half of it. Absolutely, right? We could take half of it. We could subtract, but we want a pattern that's going to work every time, and subtraction is not going to work to get us to this next one. We're not going to be able to subtract the same thing. So I do agree with the taking half of it, but I'm going to call taking half of it dividing it by 2. Those mean the same thing, right? If we're taking half of something, dividing it by 2 is the same thing. So to go backwards, 8 divided by 2 is 4. And to go backwards from 4 to 2, we would still say divided by 2. So 4 divided by 2 gets us 2. So on this one, if I want to go backwards, I could still divide by 2. So I'm saying 2 divided by 2. So 2 divided by, so we're taking this number right here. 2 divided by 2 is what? 1. Okay, and that's why when you raise something to the 0 power, it's 1, because when you go backwards, that's what you get. So to go forwards, we're saying 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. We're doubling it going forwards. To go backwards, we're dividing by 2. Same thing here. If I take 1 and I divide 1 by 2, 1 divided by 2, I'm at 1/2. If I take 1/2 divided by 2, and I'm just keep on going backwards, I'm at 1/4. 1/4 divided by 2 is 1/8. So the way that these negative exponents work is that you're going to put 1 on the top, and then on the bottom, it's going to be 2 to the first power. So that's just 1/2. We're going to have 1 on top in the numerator, and then we're going to take the, when we move the 2 to the negative 2 to the bottom, we're taking away that negative part. So 2 squared, which is going to give us 1/4. And the reason that we're getting it is we're dividing by 2 when we're going backwards. So this one is going to be 1/2 to the third, which is 1/8. Everybody kind of understand how we're coming up with that? So we'll talk about a general rule for this in just a minute. But we had a point at 0, 1, -1 1/2, -2 1/4, -3 1/8. Start out, we're going to start out really small, and we're going to get really big really fast. All right, so kind of just a note right here. Anything raised to the 0 power is going to be 1. If you have a negative exponent, so x to the negative n, you're going to do 1 over x to the n to figure out what the answer to that is. Here's what we can learn from this. So this is exponential growth. As x increases, y increases without bound. That means that it's going to go to infinity. As x decreases, so as x gets smaller and smaller and smaller, y decreases, getting closer to 0. Is it ever going to cross this axis? So in other words, if I say 1/8 divided by 2, I'm going to have 1/16. 1/16 divided by 2, I'm going to have 1/32. It's going to get closer and closer to 0, but it's never going to touch. Okay, so the x-axis, or the line y = 0, is going to be a horizontal asymptote. The graph goes through the point 0, 1, so this is the y-intercept. That's an example of exponential growth. Is everybody good with that? Okay, so the only thing that we've really changed here is now we don't have a 2, we have a 1/2. Okay, so we're kind of looking at the same type of problem. They're still telling me every time what my x is, so I'm going to jot those down. So they're asking me to take 1/2 and raise it to a power. So 1/2 to the x. 1/2 is still a positive number, but it is a fraction. So they're saying 1/2 to the third. To the second, to the first, to the 0, to the -1, -2, -3. So I'm going to start down here because this is a little bit easier to think about what 1/2 times 1/2 times 1/2 is. That's going to be 1/8. So we have a point at 3, 1/8. So it's really, really close to that x-axis. If I do 1/2 squared, I'm doing 1/2 times 1/2. And that's going to get me 1/4. I have a point at 2, 1/4. One half to the first half power is just 1/2. So 1, 1/2. So here we go with this 0 and negative exponent. So if we're multiplying 1/2 times 1/2 gets me 1/4, 1/4 times 1/2 gets me 1/8. To go backwards, we wouldn't multiply by 1/2, we would divide by 1/2. So if we're saying 1/2 divided by 1/2, you're going to end up getting what? How many times will 1/2 go into 1/2? 1, which goes with our property that we said that anything raised to the 0 power is going to be 1. If I take 1 and I divide it by 1/2, be careful because sometimes we have trouble with division of fractions. But if you type in your calculator 1 divided by 1/2 and go backwards, it's going to tell you it's 2. We'll talk about why that is in just a minute. But 2 divided by 1/2 is going to give you 4. And 4 divided by 1/2 is going to give you 8. So let's plot those points real quick and we'll talk about. So we've got the point 0, 1, -1, 2, -2, 4, and -3, 8. Look at this. We definitely got exponential decay. So we're getting smaller, and we're getting smaller really, really fast. It's similar to like if I was going to say I really want to lose weight, and I want to lose half of my pounds every day. So this would be an example of that. So I would start out, let's say I start out at weighing 8 pounds. The next day I'm going to weigh 4 pounds. The next day I'm going to weigh 2 pounds. Will I ever weigh 0 pounds? Not if I just keep halving myself. I won't get to 0. So it's going to get really, really close to this line, x equals 0, but it's never going to cross it. The x-axis, I'm sorry, that's y equals 0, but it's never going to cross it. Okay, let's talk about this issue real quick. Just so if I have, let's just do one example. We did talk about that if you have x to the negative n, that means you're going to have 1 over x to the n. So if I have 1/2, we have 1/2 raised to the -2. Let's just pull one of those out and work. How do you do the math there? Well, it would be 1 over 1/2 squared. Okay, and we know that 1/2 squared means 1/2 times 1/2, which is 1/4. Is everybody okay with that part? And when you divide fractions, remember that so if I wanted to say, well, what is 1 over 1 divided by 1/4? The way that happens is it's 1 over 1, the division turns to a multiplication, and then you flip that second fraction. And so you're going to get 4 over 1, which is just 4. But that's how that process works. Your calculator can handle this for you, though. But that's why you're getting what you're getting. Okay, so exponential decay. As x increases, the function values decrease, getting closer and closer to 0, but they're never going to get to 0. As x decreases, the y increases without bound. The x-axis, y equals 0, is the horizontal asymptote. And as x decreases, the function values increase without bound. So here are some examples of properties of exponential functions. So if a is greater than 0 and not 1, you're going to have exponential growth. Here's a whole bunch of examples of that. So 4 would be greater than 1. That's our base. 2.5, 1.8. Those are all greater than 0. But then look what happens down here whenever we pick something that when a is between 0 and 1. So things that are between 0 and 1 would be fractions, like our 1/2 that we just used. That would be exponential decay. So 0.7, that's a number between 0 and 1. 0.4 is between 0 and 1. 0.25 is between 0 and 1. You're going to have exponential decay. It's going to be going the opposite way. So these functions are continuous. They're not going to have any holes in them. Okay, they're 1-to-1. The domain is from negative infinity. From negative infinity to positive infinity. Our range, though, is from 0 to infinity, because remember, on both of these, they never go below the x-axis. So we're increasing if a is greater than 1, and we're decreasing. So this is exponential growth if a is greater than 1, if your base is greater than 1, and we're exponential decay if it's between 0 and 1. We do have a horizontal asymptote at the x-axis, which is also the line y equals 0. And our y-intercept is 0, 1, and there is no x-intercept because it never crosses the x-axis. Okay, everybody good with that? So let's talk about what happens when we start adding some things to the base. And this is where I want to go in a minute and show you guys what you're going to do with your homework, okay? But you can imagine that if I've got 2 and then raised to the x minus 2 power right here, that it's going to shift that. And it's telling us, we can already tell that it's going to either shift left or right. Everything that we've worked in the past that got shifted left or right, it was the opposite of what we thought. Do y'all remember way back when we were doing all those translations? If we were going left or right, it was opposite of what we thought. So if you're following on Zoom, put in the chat box whether you think this is going to go 2 units to the left or right. What about you guys in class? Y'all think this is going to go left or right? I think right too. We gave a pretty big clue because we just got through saying it would be the opposite of what we think, and -2 you would think would be to the left. And so I think it's going to go to the right too. All right, so our chat is agreeing with us. When you get ready to do your homework on this, it might be a good idea to go to your graphing calculator and type in your function under y equals. Our base function is just going to be 2 raised to the x power. Sometimes it helps to type that base function in so that you have something to compare it to. And our new function is 2 to the x minus 2. 2 reasons. We could use this kind of to fill out our table to get values for our x's, our y values, I'm sorry. And we can kind of eyeball on our graph what we think was going to happen. So remember that the blue was our 2 to the x and our red was our 2 to the x minus 2. It does look like it kind of got shifted to the right too, got pushed over to the right too. So I think we were okay with that. So I'm going to look at my table real quick. And here's what I was kind of talking about on the table that might give some of you guys some issues. So 2 to the negative 1 is 0.125. And 0 is 0.25. 1 is 0.5. So I'm using the red numbers because we're talking about the second equation that we plotted in, and that was those, so 1, 2, and 4. So let's go back and look. So this is what we got. So if we wanted to do this by hand, we would say, okay, we're plugging in -1 minus 2, because they wanted us to plug -1 in for our X value. And so we would get 2 to the -3. So if we do this by hand, that would be 1 over 2 to the 3rd, which is going to be 1/8. So if you need the fraction, you can get it that way. These things are equivalent to each other. Okay. When we plug in 0, we're going to get 0.25. We know that that's 1/4. We could work it the same way that we did those. We plug in 1, we're getting 0.5, which you know is 1/2. Plug in 2, we're at 1. We plug in 3, we're at 2. We plug in 4, we're at 4. So we can plot these points. This is what our new equation would look like: 3, 2, 2, 1, and 1, 1/2, and then 0, 1/4, and -1, 1/8. It kind of goes up like that. We know it gets really, really close to that x-axis, but it stops right there. Okay, so this one. Going back to think about translations. If this is going up or down, what do you think is going to happen if it's 2 to the x minus 4? If you're in chat, let's make a prediction. Is it going to be up or down? On Zoom, people. What do you guys think? 2 to the x minus 4, what is it going to do to our... Should be down, right? Because if we're going up or down, it wasn't opposite of what we thought. It was, right? It was exactly on there. So we think it's going to be going down. So we could go straight back to our graphing calculator, and we can just adjust our y equals this time. So we still have a 2 to the x, but we don't have this -2. We have a -4 from the whole thing. So when I graph it, the blue is our original and the red is our new one. So it does look like it got shifted down 4. The red compared to the blue. So if we go to our table, we could jot down the points. -2 is -3.75. -1, -3.5. 0 is -3. 1 is -2. 2 is 0, and 3 is 4. And I'm using the red numbers because that's the one that we changed. So let's go back and fill that in on our table. So when we plug this into 2 to the x minus 4, we came up with -3.75, -3.5, -3, -2, 0, and 4. So I just want to make sure that you know, like, to get this first one, what I did was I would say 2, and they're telling me to plug in -2 for my x, and then I would say -4. Well, 2 to the -2 is 1 over 2 squared, and 1 over 2 squared is 1/4, -4 ends up being -3.75, or -3 3/4. Everybody okay with that? If you had to do it by hand, that's what you would do. Okay, so we can plot these points: -2, -3.75, -1, 3.5, 0, -3, 1, -2, 2, 0, 3, 4. Okay, we shifted this 4 units down. So one thing you should notice is that we have a new horizontal asymptote because we forced this thing to go down 4, our new horizontal asymptote would be y equals 4. Okay,